Okay, cool. So kind of quick question that, or like not quick question, but like kind of what leads into us, like, hey, how do we make sure we don't have high variance or high bias, right? Like what are the things we can do? And this one big strategy essentially is to use regularization. So regularization is a really cool mathematical technique essentially that allows us to shrink down like predicted variable effects. And we're either getting rid of those features or at least downplaying their importance. So you can kind of imagine like, you know, in a little like, you know, shooting gallery, you know, scenario where the shooter essentially is the model, right? And trying to shoot like a target, you know, you can imagine like, I'm going to use, what's it called? Like when you're shooting like a bow and arrow, it's like you imagine like, you know, how far do you pull back, you know, one thing, if you guys have ever shot like a bow and arrow or done any kind of shooting, usually they tell you is like, you know, you have to like breathe and like, you know, relax yourself a little bit because if you're too uptight, basically your muscles get too tense and stuff like this. So there are other features you have to kind of consider, you know, figuring out how fast, you know, how much the wind is, how far away the target is. There's all these different features that you have to take into account. But some features are going to be more important than others, right? And some features that maybe you inherently kind of like learned by accident, like making that fake scenario of like every time there's a red person with a red shirt in your view, it means you have to like shoot off to the left for some reason. We want to downplay that or completely remove that. So that's what like regularization lets us do. And what's nice is an automated process. So we go back to our cost function. So this is where, again, we're going to use our gradient descent in our cost function. We can basically readjust our how well our model does. So originally our cost function, note that I use J here. I don't think the curriculum actually uses the letter J, but usually in most curriculum, or not curriculum, but most like text and stuff like that, you will see J referring to the cost function. So I put that in there. So remember our cost function essentially says, hey, take how your predicted value, which is y hat, and the actual predicted value, and say how well does it, basically how much different is it, the squared difference between the two. So if imagine for our linear regression, for example, we have mx plus b, where this j right here is just representing for each feature. So each feature has its own m, essentially, its own slope. Really, this should be b underscore j here too, just for the record. I'll put that in there. And there we go. So note that basically this basically is our y hat right here. And that's how we make a prediction. So what we can do with normalization is say, hey, like we don't want the model to consider like a lot of features, or we want to downplay some features, right? We want to automate this. One way we can automate this, like, well, the gradient descent is going to optimize on the cost function, J. So we're going to build in some factor essentially into the cost function. So that way we don't have to actually, like it can basically consider that while it's doing optimization. So there's two ways to do this, the L2 normal regularization and L1 normal regularization. So I think I mentioned L2 and L1 probably, but note that you'll see this a lot. Just know L2 is referring to, oh no, I'm sorry, this is another cohort I talked to, but L2 is going to refer to essentially the squared part, and L1 is going to refer to essentially the equivalent to the square, but in one dimension, which is going to be absolute value. If I said L3 norm, what power do you think that would refer to? Not that anyone uses it, but just kind of getting you guys the idea. So if you imagine L1 being like the power of 1, L2 being a power of 2, L3 norm would be a power of 3. Yeah, that's kind of like the equivalent going on here. Just kind of like, no, that's kind of like what we're doing. And essentially this is going to refer to how much we punish extreme values. So the most common one is usually ridge regression, which is the L2 norm regularization. So note that these are kind of like equivalent to each other. You might see it referenced either way as ridge regression or ridge regularization or L2 norm regularization, okay? So note that we introduce a new kind of what we call a hyperparameter lambda. And basically that's going to be put into our equation here. So you can see here, here's the original cost function. And essentially what we do here is we're including this other factor, lambda, times mi squared. So mi, remember, represents basically, you can think of it like the, what's it called? This is my train of thought. The weight of that specific parameter. So like, here's the slope, but just know that it's just the weight of that part, and we're squaring that part, just kind of like we're squaring here. So essentially we're punishing here, because what's going to happen is the cost function, we want to make that as small as possible. So if we automatically give it a boost of some factor lambda, so this lambda could be like, you know, let's say 0.5. If we automatically give whatever the coefficient is, a 0.5 boost, right? These values mi right here are going to boost it automatically. So what's going to happen is essentially we're like, well, let's make mi smaller and smaller to really optimize it. So this kind of helps prevent using larger terms essentially. And if you wrote this out in its full glory right here, you can go basically write it this way. Note the curriculum does put in some extra like notation in here, or not notation, but like different parameters, which really aren't necessary. So just kind of be aware a little bit that some of these values are actually related to these parts over here. I think they left this as like P or something like that, but really it should be related to.
There's too many, there's not the same number of left and right parentheses. So
yes, and that's another thing too, is that I think one part in this that kind of comes up is that it's sometimes kind of implied of where, like, physicists would do this all the time. They would never write parentheses in like the right summation. So like that, I'm guilty of it too. For example, like this right here really should have a parentheses going around both terms all the way through. But yeah, so just kind of know that everyone has a different way of kind of writing it. I think it comes down from background. I will tell you, when someone introduced me to this verse, they used notation that was completely backwards to like how I learned it, with like, what's it called? Subscripts and superscripts, and the superscripts describe something else. So just kind of always be careful like when you're reading these equations. But the main idea here is you should know is that basically for every feature, right, has some weight mi, right? And each of those features really should be put in as punishing that part. So like you're basically trying to punish high values. Okay, makes sense? Okay. Cool. And we call this hyperparameter. So this is a new term, hyperparameter. Basically, it's a parameter, right? Just like mi is, or b, right? So we're talking about like the slope of the different features. But we call it a hyperparameter because it's not really an important parameter to the model. It's used to help train the model. So essentially, we do this lambda here to help train the model better. So note that basically this lambda will never appear in your actual model, right? When you actually finish your model and get the best model you have, lambda will not be part of it. Lambda is just essentially used so we can train off the cost function. And that's why we call it a hyperparameter, because it's like, it's a parameter of the thing that we're training, but it's not something that we're actually going to use in the final like trained version. Okay, so note that there's going to be a whole bunch of different hyperparameters in the future, but lambda is our first one. Real quick thing about regression, basically using the L2 norm, it's mostly used to prevent overfitting, right? It's nice because it does, well, okay, one thing, a disadvantage is that it includes all features, which means it's going to be computationally more expensive. Now that might be fine in the sense of like, you know, like, okay, it's okay to be a little more computationally expensive because it's worth it. But one nice thing about this too is that because including all these features too, it's less likely to essentially remove those features. So this is kind of like mathematical reason, but the m squared part basically allows it to essentially stay alive. Like even very small values will kind of stick around a little bit. So it'll never really go to zero by itself, just by the nature of like the squared part. Also know that correlated values spread evenly on coefficients. So what's kind of nice too is like if you have a high correlation that way, it's not going to be eaten up. Like so you have feature x1 and feature x2, and they're correlated with each other. The coefficients, essentially, this mi for each one of them, will be more evenly spread between the two. Basically, one won't eat up the other one. So this can be nice in the sense that you're keeping all the features. That's why computation is more expensive. But sometimes you actually might want to get rid of features because like, hey, like, you know, we have a lot of features. I want to get rid of this stuff. L2 norm doesn't tend to go towards feature elimination. Basically, it'll just lower it really, really small, but still keep that feature in there. So sometimes then we might actually might want something called L1 norm. So here, Lasso. This is kind of fun. I didn't know this for the longest time. I just assumed like, oh, that's weird. It's called Lasso, but it actually stands for least absolute shrinkage and selection operator, which again, why everyone just calls it Lasso, right? Or just the L1 norm, right? So essentially, it's going to look exactly the same, except of doing the m squared here. We actually do the absolute value of this guy right here. And this absolute value is going to have some few uses. It's very similar, but one thing basically to know is that it doesn't, these values get punished really high, but this one will focus more on values that are closer to 0, which basically means that it'll more likely reach to 0. So what's kind of cool is that just like we say shrinkage, which is what's going on with L2, but it also has selection. And basically selection means get rid of the feature. So what's cool is that basically some of these features will actually go down to 0. Just when it goes down to 0, it's like, oh, not important, remove this from the here. So some advantages of this basically is, again, like absolute value will set to 0. So it performs estimation in selection, basically getting rid of those features, which basically gives us something called a sparse solution. So you'll hear sometimes a sparse matrix. Basically, it means that some of the values in this matrix or some of these values in the solution in this case are essentially 0. So what is nice about this is that if you have a sparse solution or a sparse matrix, you can actually do a lot more efficiency. So if you measure, when we were talking about linear regression, when you're multiplying matrices, so you imagine like this is our matrix right here, and we multiply it by like a vector, we essentially have to multiply every single row onto here in each individual time, right? So it takes a lot of computation time. Well, if you have a sparse matrix or like a sparse solution, which is like your vector here, so some of these values, like you have values and then like a 0, maybe this is 0, 0, and some values. Basically, you can do computations, say, hey, when there's a 0, just skip over it. Don't even bother trying to do computations. So if you have a matrix that has a lot of zeros in it, you essentially can make that computation a lot more efficient. So Lasso regression, basically because it gets rid of some of these solutions, can basically create this sparse solution, which might be more ideal. And note that these can actually be very similar, but instead of getting zeros, you tend to get like just very small values, which is not a sparse matrix. So that's why this can be more computationally efficient. Okay, cool. Yeah, so those are our 2 regularizations. But do you guys have any questions on either Ridge or Lasso? No, pretty good. Sound good? Thumbs up if you're feeling good. Awesome, cool. And these will be really important. And I'll kind of say, like, we've been talking about this in the context of like linear regression. These ridge regression, lasso regression, bias, and variance will be important for all other machine learning algorithms as well. We can use regularization using this cost function right here. And you can see here, here's the generic cost function right here. So this can be used for any equation, like, or not any equation, but basically we can use this for any kind of prediction. So if we predict y hat in some other way besides just mx plus b, we can essentially take that y hat, that prediction, and stick it in there. So it makes it kind of nice and easy and much more flexible. So just know that, like, even though this exists here and the curriculum kind of focuses on linear regression, we'll see this in other models too, where we can do regularization here. Cool. All right, so I guess I'll go ahead and stop recording here.